Okay, let's start the chain sync. Yeah, Misha, can you give us an update? Oh, sorry, I'm not sharing my screen.
Yes, I'm giving up on the investigation. At this point, the most likely explanation is that it's a RocksDB bug.
Okay.
And if that's the case, yeah, we need the graceful shutdown implemented.
How are those things related? I mean, if it's RocksDB bug, also you're saying it's only triggered because we don't shut down gracefully.
So if the hypothesis is that the bug, like the data got corrupted after RocksDB hit out of memory, which means that if we kill the process at some point, it could corrupt data. RocksDB.
Oh, I see. So you're saying it's basically this is caused by not shutting down near the prop gracefully.
No, it's probably caused by out of memory, but it could also be reproduced by shutting down.
Oh, I see.
Like if RocksDB didn't have a bug, it wouldn't crash like that. And if it does have a bug, then you can hit it in any way. But I also think it's possible that the bug triggered from the large, like huge transactions we did in that version. So we might be safe. Like RocksDB people would have found it if it seems like it's some kind of rare bug that we hit. So maybe it's not that bad.
We're trying to do a transaction that's 7 gigabytes large.
And I also found a bug in chain and sent a fix. And I'm gonna do a small refactor to prevent similar bugs.
How do you find this bug?
So I saw suspicious debug output. A node was saying a block was rejected because of like DB block height was not found. And it seems like nonsense because like DB block height shouldn't affect correctness of a block. Yeah, and it turns out that there was a bug in there which caused correct block to get rejected.
I see, but it's not all. So what's the trigger of that rejection?
So the first block of the epoch should like when the node gets the first block of the epoch, if the node is currently on like a fork has a small divergence with that block, then it will reject it. But then after that, if it gets the header separately, it will accept it, and if it gets the block again, it will accept it. So it gets rejected for like some point in time.
So it's temporary on the wrong fork. I see. It's interesting.
Yeah, so yeah, this bug shouldn't affect the protocol.
Yeah, but it may cause the validator to miss one block if they were supposed to produce a block after that block.
It could cause longer forks for necessary missing blocks.
Okay. Oh, it's great that we're fixing it.
Yeah, so this bug was because a chain store update for some methods of it just call chain store methods and ignore the update. And we have a bunch of other methods that do that. So my plan is to remove them from like the chain store access interface. Yeah. So we don't call them by accident.
This is what chain store update. Okay. Interesting. We didn't even notice this before. When reading from chain store update. So all the reads are wrong, basically. Almost all of them.
Like for some of the methods, they're only called by garbage collection.
I see.
And they work. I think this one method was like maybe initially implemented for something like RPC, and then later it was used by chain for like client blocks. And
I see.
That's why it was a bug.
I see. Oh, I see. So usually it's not a bug because chain store update only exists for one block. It doesn't. You don't have multiple blocks, so you don't need to read from the cache from inside chain store update.
In what case?
Oh, because usually you only construct this to apply one block, right? If you only need to apply one block.
The garbage collection, you mean?
No, I mean like when you process blocks.
Oh, but when we process a block, we apply multiple headers if we switch from one fork to another.
Oh, I see. I see. Yeah, that makes sense. I see. Oh, okay, interesting. Yeah, didn't realize that part. But yeah, so it's essentially be only related to header information because other stuff you only process them once. Okay. Yeah, that's interesting. I fixed some issue. So there's issue with migration of archival nodes for validated information, epoch validated information. In the fix for validator RPC. Yeah, basically there's some issue with validator RPC. We fixed it, but the problem is that while we're fixing it, we introduce another column, which is fine, but it causes issue because we didn't populate that column for archival nodes, meaning that people now have trouble querying data for archival nodes or querying validating information for archival nodes on the very old epochs. So it only affects archival nodes, but still is cause some problems with partners. So I was working on fixing that. Yeah, I think. Yeah, I think that's it. And yeah, let's maybe discuss this. Yeah, Alex, do you want to talk about things related to sharding?
Yeah.
Do you want to present? I can stop sharing.
Yeah, let me try to figure out my controls here.
Okay, sure.
Well, actually, also depends. What do you prefer to discuss right now?
Maybe let's talk about. Well, we can talk about multiple things, right? We can talk about either async sharding versus sync sharding, or we can talk about Well, I guess those are related, right? We can talk about how we divide the state into, into shards.
Yes.
But they are actually related. So
yes. So I can give a brief overview. I just want to give a brief overview of a particular state that I think would be cool to arrive to, and we can just discuss it first on philosophical level. Is it something we want to get to, or is it? You guys can see my whiteboard.
Yep.
Cool. Let me share it as well, in case someone wants to join. Chat. Okay, so so the particular thinking is that I see two use cases existing today, for neither of which we cater well. One use case is DeFi, in which synchronous calls are pretty important, right? So for example, if you think about the Flash loan, I don't remember how much we discussed last time and how much I was discussing in other conversations. So I will remind that the Flash loan is a function that gets an amount and a callback and sends amount to the predecessor, calls callback, checks that the amount it has is no less than A, and A is amount I have. Does that make sense? So the contract says how much money it has right now, then it says the amount that the predecessor asked for, calls the callback and makes sure that the predecessor, whatever the callback has done, Flash loan doesn't care, as long as the callback ended up in this money being reimbursed back, right? So the use case would be someone has for example, sees an arbitrage opportunity on the exchange. They borrow money, they perform the arbitrage on the exchange. As a result, they will have more than AMT, right? Because they successfully arbitraged it. So they will send AMT back to the Flash loan. And so at the end of the callback, the Flash loan will have money back. So obviously this only works if this check, which is an assert, if the failure of this assert unrolls the entire transaction, because otherwise, if this is not transactional, if this is not, if there's no consistency, then the callback can steal money, and then by the time the contract asserts, money have already been gone. Right. Okay. So this is an extreme use case. So Flash loans is an extreme end of how badly synchronous calls are needed, but generally many use cases work very well if you have synchronous calls, work very poorly if they don't.
It's pretty much the only thing that actually requires synchronous calls. I mean, everything probably doesn't need synchronous calls.
Well, an example of another thing that requires synchronous calls is, well, you know, the train and hotel problem, right? You cannot do that without locks or synchronous calls. And obviously, if you have locks, you can implement synchronous calls, right? So nothing really stops us here from, like for as long as everything that the callback is calling to is aware of the concurrency control system we're using, right? Like you can implement any concurrency control system on the contract level, on the contracts level. But even if we just consider simple use cases, right? Like you want to implement Uniswap without synchronous calls, it's pretty tedious. You either need to first transfer assets to the contract of the Uniswap and then swap within the Uniswap. Or
it's pretty logical. So Uniswap is a kind of a decentralized version of an exchange. So how do you use an exchange? You transfer assets to it, you ask it to exchange your asset for another asset, you get back your another asset, and the Uniswap on the asynchronous system can work similarly. So it can be done in a single call, but the single call would involve multiple asynchronous steps. So first transferring an asset to this market AMM, then AMM internally does the exchange. This is atomic because it's within AMM. Then AMM sends another asset back. Well, in Ethereum, it happens in the same way, just it's all within one transaction. So in Ethereum, it's all synchronous. So for example, you can roll back the entire transaction if, well, for some reason, for any reason. In an asynchronous system, you can't roll back the entire transaction, but you still can do it in a single transaction. So basically, AMM receives the tokens and a request to exchange those tokens. It does the exchange at the current rate and send the exchange token back to the caller or to some different addresses if one was specified. And well, there may be some issues. For example, the rate might change. Well, in Ethereum, the rate might also change because when you send the transaction, the state of the chain might be different than the state when this transaction is executed. So there is also some asynchrony even in Ethereum. In Near, there may be a bit more asynchrony, but AMM can also implement kind of limit orders when you specify limit on exchange rate, and if it can't get, you can't get this exchange rate, then it will just send your initial token, original token back without doing the exchange. And all of this can be done asynchronously. I don't see any problem with implementing AMM in asynchronous.
Right. So that works if my use case is actually swapping tokens, right? Uniswap is used for way more than that, right? Specifically, in Ethereum today, Uniswap enables you to do many use cases where you come there and you say, and you have Ether, right? And you want to perform something that requires DAI. So you swap Ether to DAI, you perform that. If you failed to perform the next step, you do not lose anything. Now, if it is asynchronous, you swap Ether to DAI, you want to do something with DAI, and it fails, well, the only thing you can do now is to swap back, right? That could easily be associated with some losses, right? So this is exactly what synchronous calls give you. They give you an ability to compose getting loans, swapping from one asset to another, etc., and then performing some actions, and only taking advantage of those swaps and loans, etc., if whatever you wanted to do has happened. And if it did not, well, you lost your gas, but you did not lose anything else, which is critical, right? So Uniswap is used extensively as a composability component in use cases where you need to do something with assets you don't have, which would not work as well with asynchronous calls.
Yes, so this kind of thing, well, it requires everything to be synchronous. In fact, there are problems actually. There are many possible attacks. For example, flash loans. When I hear about flash loans, I, in most cases, hear the flash loan was used to attack some DeFi app.
But it is not, flash loan did not enable it, right? Someone who had those money would also attack the DeFi app. So flash loans just, like, the app is vulnerable. The flash loan allows to show this vulnerability. If flash loan does not exist, the app does not become invulnerable suddenly, right? It just becomes more expensive to attack it, but it is still as attackable because the person who possesses the money risks exactly as much, right?
Yes, but with flash, like, moving large sums of money without like being traced is difficult. So for attacks with flash loan, they don't need to move large sums of money from like their account that is connected, that can be connected to their identity. So it's not just someone who has money. It's difficult to somehow to move it in such a way that it can't be traced back to them, because all those stuffs like various mixers, they either you lose anonymity if you try to move too large amount, because like if it's exceeds it becomes comparable to the total amount that all that mixer's users move through it, then you become to stand out. Or they have like fees, so someone who is moving those large sum will also losing large sum on some sort of fees. So it's not just the attackers to attack. Yes, so if attack becomes significantly more expensive, it's good because it becomes significantly more difficult to conduct such an attack.
Okay, I hear you. I understand your point. I still believe that we can discuss it separately, right? I don't think that people who understand DeFi the best in our company are on this call. So
Igor, do you want to say something? I saw that.
Yeah. One thing I noticed that this kind of synchronous islands kind of a lot reminds me of something like sidechain. So maybe it's the solution.
What is fetching?
Sidechain.
Oh, sidechains. Sorry, sidechains. Yes. With the difference that synchronous islands, they're more deeply integrated and use more security of the chain. However, I'm not proposing to do synchronous islands. I'm proposing to do one synchronous island.
Mongo is kind of like synchronous island.
Problem is that if we're going to have a single synchronous island, we are going to have something like Ethereum when every transaction costs at least a couple of dollars, because the throughput of a single synchronous thing is limited. So
okay. But then, so if that happens, if it does happen that our island becomes too populated, and it takes a couple of dollars to process, that's when we can build Moonglow. So I will very briefly tell what Moonglow is.
Moonglow is basically also one big synchronous island. I mean, right. Where everything is synchronous is a synchronous island. We call it Moonglow, whatever. Still, if you still need a single machine to process everything, then it can't be scaled.
Yes, but that's an expensive machine, right? And it is I don't necessarily believe that processing every transaction that you would want to be processing in the synchronous island will eventually cost $2. Like assuming that we are actually not staying in the same place and improving the performance of this single island, and like if it is viable to get it to like 2,000, 3,000 TPS or more with Moonglow, it is hard to believe that there is going to be sufficient
also
usage.
We are getting centralization because of those expensive machines. They're not that easily available, and
well, the point. So first of all, they're pretty easily available, right? It's but also depends on what you mean by centralization, right? You will always end up in a situation where consensus is owned by a very small set of people. That's the power law, right? Like Bitcoin and Ethereum today controlled by how many? 4 entities that can at any point, double sign. Similarly, any proof of stake system, it doesn't matter if it has 50 nodes or 14,000. There will be 7 of them. Like today, on near today, it's 9, right? That controls 33% of stake, and so in theory can double sign. So consensus will always be in the hands of few people. So the question is verification centralized? So for example, in Solana, the problem that I think is relatively critical is that in order to verify the chain, you need to run an expensive machine. So that's the property of Moonglow, that in Moonglow, verification happens on a cheap machine. Only the node that is actually constructing the chain needs to be expensive. All the verifying nodes can be cheap, right? So there is a centralization concern with approvals, but that is a very orthogonal problem, which is very hard to solve. But there is no centralization of verifying the ledger. Does that make sense?
Yes, but I still think that at some point we may want to scale past this, even those expensive machines. And full sharding allows us to scale almost infinitely. Like we
Right.
can,
So,
with
so
full
that's exactly the
sharding,
question, right? The question is, what
we
is the
can
use
process-
case? Right. Because the second use case, which I see is like to actually run applications. So it would be great if we had infrastructure in which you can deploy some application which is not a financial first, right? So their full sharding would have helped, but what it does not, because it's still too expensive, right? So like if I want an application in which like the cost of hosting is almost comparable to hosting on a centralized cloud, then I can start deploying applications there which are not owned by any centralized entity. The problem is that we cannot do it on the blockchain today because it's too slow and too expensive. So let me quickly, I don't know if we actually want to end in 3 minutes, but if we do, let me very quickly in 2 minutes present like the high level of something we can do. So again, so I will start by saying, well, let's say it's given that we have a single shard or Moonglow that is synchronous, and this is where all the payment transactions happen. And whether it's single shard or Moonglow doesn't matter. We want every block producing node to verify it. And so therefore, if the block is produced and it has 2/3 of approvals, stake weighted, they verified every transaction in the synchronous island. So synchronous island, we can think about it as not sharding at all, but the main chain, which is not sharded. And for sharding, what I want, one idea how to do it in a way that is suitable for applications, but completely unsuitable for financial use cases, is you say that you have some number of shards. Let's say it's equal to 200, for example, for starters. So you sample from you have the list of validators of all the people who want to become validators with their stake, right? So it's some sort of proposals, which is vector of stake, whatever, account ID stake, sorted by stake descending, right? So if the first 100 from here, or whatever the number are block producers. And then you sample the next 6n or 5n are going to be validating shards. So what we can do now is we can assign 3n of them. Right. So you make half of them to be explicitly assigned to the shards and be corruptible, and half of them to sample locally. So the way hidden validators sample in the Nightsheet paper. And so with this, and those are cheap guys. So they don't need to validate more than one shard. They're validating one shard. Each of them has exactly one shard assigned to them. And so if they run on bare metal, the cost of every shard is 6x of bare metal cost, which is comparable to what AWS is charging, right? So now, because those three are very corruptible, we cannot assume anything about the safety, right? So first of all, we can use a consensus which does not have a 1/3 threshold for safety. We can as well use consensus which has no threshold for safety. Well, with 3 people, actually, we cannot have any threshold for safety. But we still use something that has meaningful threshold for liveness. So, like, for example, if one of them is down, it's still operating. We can also make it 4. Anyway, and so one thing that is of question here is what happens when it is actually corrupted.
Cost will certainly not be 3 times bare metal, because first they will probably themselves use some sort of hosting like AWS rather than bare metal, and then there is a cost of actually maintaining those nodes, which may be significantly higher than the cost of operating the hardware.
But potentially, unless we design it in such a way that it is okay to go down every now and then. Right, in which case your cost of operation could be as low as just launching it. And So for example, my node that I run on Near, I have 0 cost of operation, and I have 95% uptime. So it's the worst uptime of all the nodes that exist by a large margin. If you order, the next one is 98, and that guy is also not particularly great. Right.
Okay, I think we're kind of
Yes,
running
we're
out of time. We'll have to, yeah. We can keep discussing this I think later this week.
Yeah, cool.
Yeah.
Bye bye.